Okay, hi everyone. We're going to be starting part two of proteins and peptides, and this unit and module is going to be focused on the chemical and biological synthesis of peptides. So from the first, part one that we looked at really the amino acids units themselves, right? So now we're going to be talking about larger and larger molecules, which are peptides and which are comprised, as you know, of amino acids. Okay, so like we've done with the previous section, we are going to actually divide this up into three sections, and here's the outline. So we're going to look, first of all, before we start making peptides, we're going to talk about the energetics of peptide bond synthesis. Once we do that, then we'll talk about the biological synthesis of peptides, and then finally chemical synthesis of peptides. And the chemical synthesis of peptides will be subdivided into three different parts. So in total, we'll have 1, 2, 3, 4, 5 different parts. Okay, so as I mentioned, today we'll be focusing on the energetics of peptide bond synthesis. Okay, so before we talk about how peptides are formed, here's just a slide showing a macromolecular complex, which is what we have in our bodies. And this is the macromolecular complex called the ribosome. So the ribosome, as you know, is comprised of RNA. It's actually around 2/3 RNA, and it's comprised of around 1/3 proteins. It has around 30 to 34 different proteins. And this big complex here is responsible for making proteins and peptides. So this encompasses, the biological route, and we will look at how, transfer RNAs can direct the correct amino acid to the right place at the right time. In contrast, we'll be looking at a different strategy here, which is a more purely chemical model, right, in which you mix different solutions and different chemicals together. And how is it that we can use chemicals to generate the same peptide? And we'll talk about and compare the advantages and disadvantages of everything. Okay, so before we talk about peptides, we need to first understand that peptides are really the union of amino acids that come together. Okay, so last unit we talked about amino acids, and I'm just drawing these charges in a little stronger because they were a little hard to see. So recall that we have a Zwitter ion here. This is alanine with an NH3 plus O minus. So this is the charge at physiological pH. Here we have an amino acid called cysteine. It's a CH2SH. And if these two amino acids were to come together, well, a couple of things have to happen. You have to remove the positive charge on the nitrogen by removing one of the protons. Okay, so this would have to become neutral. And then once this becomes neutral, this cysteine, if it's to come together, it's going to have to find a way to react at this carbonyl group. And you can imagine after proton transfer and removal, we're going to get the removal of an oxygen here and then a couple hydrogens. So the net effect is that we're going to get loss of water when we bring these two groups together. So this is referred to as condensation. And the net effect is that we observe, or we get, a peptide bond. Okay, and this is your new bond here, also known as an amide bond. So you can imagine you can do this multiple times. And conversely, you could do the reverse reaction, which you would think of hydrolysis, doing the reverse reaction. So water would come in and actually attack the amide bond, and you would get release and break that peptide bond. So you'll hear me say peptide bond, amide bond interchangeably throughout this unit, and they really are the same thing. What else can I tell you about peptides? So peptides, are typically what we call short oligomers, and the definition of a short oligomer is roughly around, 5 or 10 amino acids to around 50 or 60. Okay, so here I say around 20 to 50. You could go as low as 5 to probably as high as 75 amino acids, and that would still be called a peptide or a polypeptide. In contrast, proteins are usually much longer and bigger molecules, and this is usually something that is around 50 amino acids to 3,000 amino acids. So there isn't like an exact cutoff of, the 51st amino acid or a 75th amino acid. If you're dealing with a molecule that has around 60 amino acids in length, and if that is a full-length protein, then people will probably call that a protein. But if that 60 amino acid peptide is a fragment of a protein, then you'll hear researchers typically refer to that as a peptide or polypeptide. Okay, so let's talk about the reaction of that molecule. Okay, how do we make peptides? So at first sight, this seems like a very simple carbonyl substitution. All right, so let's draw our carboxylic acid, and let's draw our amine. So an amine and a carboxylic acid have to come together. All right, now what we want to have happen is that we want this electron from the nitrogen to come and attack this carbonyl. However, there is a problem associated with this. This carbonyl group here is actually not a very good electrophile. And the reason it's not a very good electrophile is because you actually have good electron density going into that carbonyl ring. So I'll just bring this down a little bit so you can see. So carboxylic acids are not good electrophiles. Okay, this is due to resonance. So I'm going to draw my double-headed arrow here. And here you can see that through electron delocalization, you can now have this species that looks like this. All right, so not the best resonance structure or not the best electrophile. The other thing that makes things a little more challenging too is that not only is this a bad electrophile, you actually get the amine from the nitrogen reacting with this proton here. So if you recall, the proton attached to a carboxylic acid, the pK of that proton is roughly 2 to 5. So it is fairly acidic, meaning that this nitrogen here, which has a pKa, whose conjugate acid has a pK of around 9 or 10, is actually in a very, very likely and good place to remove that proton. So in fact, the more likely reaction that's going to happen is simple acid-base chemistry. Okay, so what you're going to do is you're going to take, again, your base. This is your acid. And instead of doing the condensation reaction, you're going to do acid-base chemistry. So what you're left with now is the conjugate base. Plus, you're going to be left with the conjugate acid. So what you can see here is that, well, there's been no amide bond that's been formed. And furthermore, this conjugate base, the carboxylic acid, actually now has an even stronger resonance form because of that negative charge. And what that means is that through electron delocalization, that this carbon here is now a very poor electrophile. Okay, so by acid-base chemistry, we've now made the desired carbon a very poor electrophile, very hard to get into attack. And then furthermore, we've gone from a good nucleophile, nitrogen is a good nucleophile, to something that now has a positive charge on the nitrogen and doesn't have free electrons. So this is now a poor nucleophile. Okay, so we're in trouble here because acid-base chemistry governs this, and we can't make our desired peptide bond. So that's number one. At first sight, simple carbonyl substitution. So both starting materials and products are stable. Number two here refers to the product, the amide bond here. And you've probably heard of amide bonds or peptide bonds exhibiting what is known as sp2 character. And what this simply means is that the amide bond is heavily delocalized because the nitrogen electrons are very willing to donate its electrons into this species here. So as you can see here, this is a delocalized system here. Amides are delocalized and stable. And conversely, these bonds are actually very difficult to hydrolyze. But that's actually good for us because we know that proteins are the real building blocks of the cells. This slide here just shows a lot of what you've learned already in first year biology, that peptides can form classically structures known as beta sheets or alpha helices. These are really structures that are held together through hydrogen bond networks and are very, very stable structures. Okay, so let's take a look more closely at amide bond formation and degradation. So I've mentioned to you that the carboxylic acid and the amine are stable, and this is your desired reaction, amide bond. Okay, and in order to go from your amide bond, you got to hydrolyze it. Okay, if you think of this from a thermodynamic point of view, both of the products and the starting materials are stable. Okay, so it's actually, when we think of thermodynamics, this reaction here actually has a change in delta G of around 0, meaning that the overall reaction is thermoneutral. There isn't anything really there to drive the reaction. It's not a downhill reaction, nor is it an uphill reaction. And the other thing we talk about too when we're discussing reactions is kinetics. Okay, so it's a thermal neutral reaction, no real driving force too. And again, just to emphasize this is again a very slow reaction. It's very slow because you predominantly get just simple acid-base chemistry, as we've clearly discussed in the last couple slides. Okay, but when I'm saying slow, what I mean is that if you actually put these two things together in a vial and you test this reaction after a day or a week or a month, you're not going to get your desired product. Okay, however, if you do have a lot of time on your hands and you do add a little bit of heat, we're talking about years, okay, then you can maybe slowly start to get your product. So let's take a look at what that would actually look like, from a reaction coordination point of view. So here is your carboxylic acid. Here is your amine. So when this comes, this has to come and react at the carbonyl group. And we're going to attack the carbonyl group, break the pi bond, so electrons go up to the oxygen. Your nitrogen, because it has attacked, now has 4 bonds and is positively charged, and this is known as your tetrahedral intermediate. Okay, and then after some proton transfers, this pi bond will reform from the oxygen and you will release the OH group. Okay, and what you will generate after deprotonation is your peptide. Okay, and here we have our starting materials. Okay, so you can see that getting to that tetrahedral intermediate is actually very difficult. We've talked about some of those issues already. Just call this Ti, tetrahedral intermediate, and as you also know, this is a reversible reaction. All right, so if we're thinking about a reaction coordinate diagram here, what I want to highlight for you is we're going to be looking at delta G, and we're going to look at the energy of our starting material. Okay, so let's label that SM, starting material, starting materials, and let's look at our peptide or our product. So I've already told you, we've already discussed that the starting material and the product actually have around the same energy. Okay, what about the energy of the tetrahedral intermediate? It's a very high energy compound. It's very difficult to get to that structure. So that's going to have a very high energy. Okay, we'll call that Ti. Okay, so in order to make your product, you need to have enough energy to get to the tetrahedral intermediate and then eventually get to the product. So what I'm going to show you is the amount of energy that you need for that forward reaction. Okay, so we're going to call this E, activation energy, F, activation energy for the forward reaction. Okay, so that's high. It's quite high. You need a lot of energy. Now let's think on the other side. If you have the product and you want to hydrolyze it, you still have to get to that tetrahedral intermediate. So the energetics of getting to that tetrahedral intermediate is also high. Okay, so we're going to call that activation energy for a reverse reaction. Okay, so this is a little bit of a problem, right? Because we need to find a way to potentially generate these products or hydrolyze them in an easy fashion. So let's think about some ways that we could help this process, right? So if you think of, reactions that you may have done in the lab, or, if you are, for example, at home, cooking something, right? Well, when you're cooking something, you're adding energy to the system, right? Because you want to cook your product, your meal, in a time effective fashion, and you don't want to necessarily wait, days or weeks to do that. So how do we overcome this energetic barrier? Well, the most common way to do this, of course, is to add heat, right? So you've done this in organic chemistry labs, you've done this at home on the cooking stove. You can even think of the first biomimetic synthesis, right? When we had the making amino acids from electrical discharges, there'd be a lot of energy needed for that to happen. However, if we're thinking biologically here, we know that cells in our bodies, we operate at very fixed temperatures, right? 37 degrees is our optimal temperature. We can't heat our cells up. There are some very small, limited number of organisms that are called thermophiles, and they can function at higher temperatures, like 72 degrees. However, those are, really, really quite rare. So in general, heat is not a viable option to overcoming that energetic barrier that we're talking about. What is another thing that we could do? Okay, here's our delta G. I'm just going to show again sort of that, here's your tetrahedral intermediate, and we need to get to our product. What else could we do to lower this activation energy? Well, instead of trying to add heat, okay, to basically go up this roller coaster here, we could try to raise the energy of the starting material, okay? Okay, so we could do something called activate the acid. Okay, so we could activate the acid to something that is similar, but is a different structure. And if we do that, if we're starting with a less stable structure, then you can see here that the activation energy is now less. Okay, so you're starting like on a hill already. So imagine if you're climbing a mountain, right? If you're starting right from the bottom, you know, that's really quite difficult. But if someone gives you a boost halfway through and drops you off, well, all of a sudden that becomes much more manageable. So this is what we will call an activated carboxylic acid. Okay, so we can activate the acid, and this reduces the activation energy to get to the transition state. Okay, so so this is actually the system that biology uses, and later on we'll talk about what chemistry uses, but it's important that we understand the energetics of that. Now we're going to talk about activation of the carboxylic acid. So let's talk about a couple examples here. So carboxylic acid, very stable structures. One way that you could generate very reactive compounds is to go back to the fundamentals of organic chemistry. So you may recall things like acyl chlorides and hydrides. Those are very reactive functionalities. You can make these in the lab using things like PCl3 or PCl5. You can dehydrate carboxylic acids to give you anhydrides. So this, in theory, could work, right? However, these species here that I've described are just simply too reactive in a biological setting, or too reactive. Okay, so I want you to think about, you know, well, I'll tell you about Goldilocks in a little bit, Goldilocks and the Three Bears, but you know, these are just too hot. They're too hot to handle, right? So yes, you'll get your product, but they'll start reacting with all these other things, so it won't be very productive. Why is the energy of the acid raised? Well, we already talked about that. That is to overcome that activation energy barrier. Okay. So let's talk about carboxylic acid derivative reactivity. All right, so you've learned in second year carboxylic acid derivatives, and this is a trend here that we're going to talk about with respect to comparing stability to increasing reactivity. So we just talked about acyl chlorides and anhydrides, and I just told you that these are two high energy compounds. They're actually very useful in the organic chemistry lab. But yeah, they're very reactive and you don't get very good selectivity. So as you move here, and if you go to the other end of the spectrum, you can see here that low energy compounds like our carboxylic acid and our amide, these are too low energy. They're very stable. They're just, you know, we call them rocks because they're just super stable and they're not going to degrade or react. Unreactive. Okay. And again, our problem is that we're starting with something here to give something that's very similar in stability. So if we look at the middle of this curve, okay, or this middle of this chart, there's an area here that actually might work. So if you go from two high stable compounds, as soon as you start introducing a sulfur and an ARB group, this is called a thioester. This is actually, it's reactive, but it's not like super reactive, okay? We've increased that energy, but it's not gonna start reacting with every single thing. This here is a phosphate ester. This is also very good. This is actually what biology uses to activate carboxylic acids. And this here is a regular ester. So, so as you go from left to right, you increase the stability, but you decrease reactivity. And conversely, as you go from right to left, you decrease the stability, but increase the reactivity. So the story of like Goldilocks and the Three Bears, if you're not familiar with that story, it's about a girl who goes into the forest and finds an empty cabin. And then inside of the cabin, there are 3 bowls of porridges. And one of the bowls, the porridge, she tries, it's too hot, okay? She goes to another one, and that porridge is too cold. All right. And then finally, she tries a third bowl, and that one is just right. Okay, so you can think of these compounds I've just circled here as being sort of just right and are the right balance of reactivity and stability. As you know, the effect of carboxylic acid stability depends on inductive effects. So electron withdrawing groups, the bigger the inductive effect, the greater that wants to leave. So that's why like acyl chlorides, things like oxygen and hydrides have a bigger inductive effect compared to like nitrogen or sulfur. Resonance in the derivative is also really important. Nitrogen is more willing to donate its electrons, so you get good electron resonance and density with that group, making them more stable. Okay, so an amide here, as we just talked about already, has very good strong resonance forms, as does esters and especially carboxylates. And then finally, leaving group ability, chloride anion is a very good stable leaving group. Anhydride, if it leaves, you get this carboxylate. And again, this is stable because of resonance. That's better compared to thiolate, alkoxide. And then a negatively charged, like amide, is actually not a good leaving group. Okay, it's just too negative and not stable. So nature uses acyl phosphates, which are here, esters for the ribosome, and thioesters to actually make peptide bonds. Okay, so now you understand the energetics of this. The last thing I just want to talk about in this energy unit with respect to peptides is just talking about catalysis, right? So you've learned in organic chemistry or many other classes in chemistry that you can also reduce the activation energetic barrier by using a catalyst, right? So you can also do this. You could use organic catalysts potentially to bring that down. There are ways to do that, but what nature uses typically is to activate that carboxylic acid, like we've just shown. Another problem with amino acids, I just want to finish here, is that if you do add heat and try to get these you just say, okay, I'm just I don't care about 37 degrees, and I'm working in a lab, so I'm just going to just crank this up to a couple hundred degrees. The big problem is that you're going to have issues of selectivity, and you're just going to get amines reacting with different carboxylic acids at different places, and then you're just going to form like 6-membered rings that don't look anything like peptides, and so this doesn't actually occur in nature. Okay, so that concludes this unit on the energetics of peptide bond synthesis.